Every single day, over 100,000 commercial flights take to the skies, and almost every single one of those flights relies on a machine built by one of two manufacturing giants, operating under entirely different engineering philosophies. In the United States, you have Boeing. Operating out of the Pacific Northwest, they established the blueprint for modern commercial travel and spent decades as the undisputed king of the industry. Across the Atlantic is Airbus. Operating out of the city of Toulouse, France, they formed as a collaborative European consortium designed with one highly specific goal: to break the American monopoly. The financial stakes between these companies dictate the global economy. When an airline chooses an aircraft, they are committing billions in capital and locking their business into a strict 20-year ecosystem of pilot training and mechanical maintenance. People constantly argue over which company builds a better airplane, but better is the wrong framework. Superiority in aviation depends entirely on who is evaluating the aircraft. To accurately declare a winner, we have to isolate the variables. We need to grade these machines through the eyes of the accountant balancing the books, the pilot flying the route, and the passenger in row 32. At the center of this rivalry is a strict engineering trade-off. It is a choice between granting the pilot ultimate manual authority or relying on software to enforce strict safety boundaries. This quadrant chart maps out the historical design philosophies of both companies, showing where they sit on the spectrum of legacy control versus modern automation. Boeing occupies the space of tactile control. Their engineering prioritizes historical fleet integration and relies on the pilot to physically feel the aircraft. Airbus occupies the space of software protection. Their designs prioritize hard computer limits, fly-by-wire commonality, and modular airframes. This specific engineering divide dictates every hardware choice and line of code on the flight deck. It is the primary reason an airline chooses to buy from one over the other. For an airline executive, the battle is fought in the narrow-body market. The financial health of most global carriers rests on the workhorses of the sky, the Boeing 737 and the Airbus A320. The 737 utilizes an airframe design dating back to the 1960s. It sits low to the tarmac. That physical restriction limits how large Boeing can make its modern, ultra-efficient engines before they scrape the runway. The Airbus A320 was designed decades later. Its taller, modular stance allows mechanics to easily integrate high-bypass turbofan engines required for modern fuel efficiency. Airlines face a strict financial trade-off comparing total ownership cost against long-term route flexibility. Boeing offers massive savings for existing fleets, requiring almost zero mechanic retraining. Airbus carries huge upfront workforce retraining costs, but offers superior future-proofing for engine upgrades. For the airline, the superior plane comes down to a business calculation, trading the immediate financial cost of integrating a new system against the value of long-term technological adaptability. Step into the cockpit, and the difference between Boeing and Airbus becomes physical. The pilots literally feel the engineering divide in their hands. Boeing uses a traditional yoke system. It links mechanically to the wings and to the tail, creating physical resistance in the cockpit, based entirely on raw aerodynamics. The trade-off is physical workload. The yoke demands constant input during manual flight and relies on the pilot to respect the airplane's structural limits. Airbus removes the yoke entirely in favor of a side stick. It communicates with strict fly-by-wire software that enforces hard limits. If a pilot aggressively pulls back on the stick, the computer will automatically intervene to prevent the plane from stalling. The trade-off for that safety net is authority. In extreme scenarios, the pilot is stripped of the ability to manually override the computer's predefined parameters. Looking at this split-screen comparison table, the core friction between manual airmanship and computer automation is clear. Boeing trusts the pilot to save the airplane. Airbus trusts the system to save the pilot. For the person buying the ticket, engine clearance and cockpit authority are irrelevant. The passenger perspective prioritizes cabin width, jet lag, and overall ride quality. On a standard domestic route, the Airbus A320 has a slightly wider fuselage than the 737. That baseline advantage gives passengers roughly an extra half-inch of seat width. But the true passenger battle takes place on intercontinental routes, pitting the wide-body Boeing 787 Dreamliner against the Airbus A350. Both aircraft heavily rely on lightweight composite materials rather than traditional aluminum. This matrix tracks physical comfort metrics of modern composite jets against older metal aircraft. Because composites do not rust and are stronger under stress, the cabin can be pressurized to 6,000 feet rather than the 8,000 feet required by legacy aircraft. This creates a direct biological trade-off. The combination of thicker air and higher humidity drastically reduces jet lag, dehydration, and physical fatigue on 14-hour flights. While passengers experience massive improvements in their physical comfort, airlines must implement specialized, highly expensive maintenance protocols to detect and repair damage to the carbon fiber structures. When you pull all three perspectives together, the verdict on the biggest rivalry in global business becomes highly specific. This final scorecard maps out exactly who benefits most from each manufacturer's approach. Boeing is the correct choice for airlines deeply entrenched in legacy infrastructure, and for pilots who prioritize tactile aerodynamic feedback during manual flight. Airbus wins for new carriers building fleets from scratch that require modular adaptability, and for operators prioritizing strict fly-by-wire system commonality. For the long-haul passenger, it is a stalemate. The 787 and the B350 both offer incredible, identical reductions in travel fatigue. While their methods for solving aerodynamic problems are completely opposed, both companies consistently execute at the absolute pinnacle of human engineering. The true winner is the global traveler. This constant pressure to out-engineer the competition makes commercial aviation the safest form of transportation in human history.